Hi, this is Eric with Math from the Gut, and welcome to part 2 of test driving the Pythagorean Theorem. So, what's the plan? In this video segment, I will introduce the Pythagorean Theorem and show 2 examples that I'll use in upcoming videos. We'll also visit the Pythagorean Theorem in a different form. Warning! There are many other videos and books that already provide examples with numbers. Please, feel free to check them out if you're still confused after watching this segment. On the other hand, I recommend watching this even if you're comfortable with using the Pythagorean Theorem, since I'll introduce some ideas along the way that I'll be using later. As mentioned in part 1, we start with a right triangle that has legs of length x and y and a hypotenuse of length h. The Pythagorean Theorem tells us that h squared equals x squared plus y squared. Let's do an example with numbers to see how this works. Let's say that the upper dot is 4 feet to the right and 3 feet above the lower dot. This means that x equals 4 feet and y equals 3 feet. In order to determine the straight line distance between the two dots, in other words h, we can use the Pythagorean Theorem. But first, let's say a few words about squaring. Let's start with a square whose sides are all equal to 3 feet. In this case, the area is called 3 squared, since we're basically taking a length of 3 and making a square out of it. This area equals 3 times 3, and we can easily count 9 square feet here as follows. Note that each one of those little squares is 1 square foot, since they're 1 foot on each side. Since 3 is being multiplied twice to get the area, we can also call it 3 raised to the second power. But usually, we just say 3 squared. Obviously, 3 squared gives us 9 square feet, which can be more easily written like this. So, back to our example. Substituting 4 for x, we get 4 squared. Plugging in 3 for y, we get 3 squared, with the result being that h squared equals 4 squared plus 3 squared, which equals 4 times 4 plus 3 times 3. Notice how I use the asterisk to represent multiplication here instead of x, since x, of course, is already used for our back and forth or horizontal length. This then equals 16 plus 9, which is 25. So h squared is now equal to 25, and the value of h that makes this equation true is the length of our hypotenuse. You may have already figured out what h is, but before we go there, I want to talk about square roots. First, note that in math, the word root refers to the solution of an equation. Think of it as getting to the root or solution of the problem. So then, the term square root refers to the solution or root of the square equation. In our example, we have the square equation h squared equals 25. So the value of h that solves this equation is called the square root of 25. In other words, the root or solution of the square equation that equals 25. It is written like this by using something that looks a bit like a division symbol. And in fact, we're actually looking for a number that divides into 25 in a special way. To find the square root in this example, we need to think what value of h, when multiplied by itself, gives us 25. Or, thinking back to the physical square, we are seeking the length of a square that has an area of 25. How about an h of 4? Well, when we square 4, we only get 4 times 4 or 16. So that's too small. Let's try something higher. How about an h of 6? Well, an h of 6 gives us 6 squared or 36. So that's too large. It turns out that our correct answer, 5, is right in between 4 and 6, since 5 squared equals 25. So, just like the Goldilocks story, 5 isn't too small, it's not too big, it's just right. So, completing our example, we now see that h, the length of the hypotenuse, equals 5. You may have already noticed that squaring and square rooting do opposite things. and we'll discuss this in more detail in part 3. Now, let's find another way to write the Pythagorean theorem. We start with our original equation, and then remember that the solution h to this equation is just the root of this square equation, or in other words, the square root of the value on the right-hand side. Just before, we took the square root of 25, which was 4 squared plus 3 squared. Now, we have the more general expression, x squared plus y squared instead. So rather than taking the square root of 25, a simple number, we now take the square root of the quantity x squared plus y squared, like this. So this is a more direct way of expressing the hypotenuse length of a right triangle. Now, let's try one more example using this new equation. Let's say that this is another right triangle and we want to find the length of its hypotenuse. We start off with our new equation and then plug in 12 for x and 5 for y, like this. Then, knowing that 12 squared is 144 and 5 squared is 25, we add 144 and 25 to get 169. Finally, we determine that the square root of 169 is 13, since 13 squared is 169. Therefore, the hypotenuse of this triangle is 13. So we have laid the groundwork. If you follow these two examples, you should be ready to do our first test drive in part 3. The test drive that we touched upon in part 1, where one or both of the legs collapse to a 0 length. However, if you're not yet totally comfortable, I strongly urge you to seek out other videos and practice more examples before continuing. Throughout all of this, you may need to hit the pause button to think or even repeat things at times. This is perfectly normal and expected. Remember, this isn't a race, and I'm really hoping that these videos encourage you to think about things more and more on your own, at your own pace, and in your own way. Once again, please leave comments, good, bad, or indifferent. They're all helpful. See you in part 3.